As you just heard, I'm Mark Röchlin, and this is a joint work with Kasper Rasmussen and Ivan Martinovic, my supervisors at Oxford University, and I'm going to be talking about device pairing at the touch of an electrode. So before, you might be familiar, or I guess most of you are familiar with the problem statement of device pairing. So device pairing is essentially the bootstrapping of secure communication between two previously unassociated devices. And in that process, they have to derive a mutual secrets without having any prior keying material or shared knowledge. This task is particularly crucial if there is no trusted third party, because the devices have to establish their identities towards each other, otherwise they don't know with whom they're talking to. And this can be subverted by an attacker if not done properly, and usually that's why the devices usually resort to a so-called device pairing protocol. There are many existing device pairing schemes found in literature, but most of them actually fall into two categories. The first one is that they require certain physical assumptions on the communication channel, which one example here is near-field communication. So if you implement device pairing with near-field communication, usually assume that the signal decay is so high that the devices can only be paired if they're right next to each other. The second category uses an auxiliary channel that is usually thought to be not accessible by the attacker. But this also immediately entails that the user needs to do some sort of security relevant decision. One example for this is a short string comparison. We've probably all been facing this problem. You have to compare two strings that are displayed at the devices you want to pair, and you just have to confirm whether it's the same string or not. And if it's indeed not, but the user makes the wrong decision, then the pairing scheme does not give any guarantees anymore. So what can we learn from literature? The desirable properties have minimal user interaction, have a very simple interface, and also make minimal assumption on the communication channel. So to set out with this, we tried to come up with a device pairing protocol that fulfills these requirements. And our idea was to come up with a scheme that allows the devices to be paired if they are being held by the same human at the same time. Because we think if a human has physical access to both devices at the same time, there are very little means or ways how you can actually prevent him from pairing them. Also, our scheme is not very taxing at the communication, or we need to make very little assumption on the communication channel itself. So how does such an approach work? So we assume we have two devices, device A and B, or Alice and Bob. They share two communication channels. One is an unauthenticated wireless channel, and the second one is a body channel. So which is established as soon as a user, as you can see on the picture, a user touches both devices, which can be a conductive surface or also a very small electrode. And this channel is established as soon as the user touches both devices. This usually works with a technology called capacitive coupling that I will actually explain right now. So yeah, this is in electrical engineering. This is quite a relevant topic that's been researched for a few years now. It's called interbody communication. There are three main ways. The first one is galvanic coupling, where the transmitter introduces a small alternating current into the body, and then a receiver picks up the voltage change. Unfortunately, this only works with very small transition systems, like about 30 centimeters on the body. The second one is surface wave techniques, and they're very similar to conventional like radio frequency transmission. You could think of using the body as a waveguide, which helps with the transmission. Unfortunately, this can be heavily affected from outside external electromagnetic waves. The third one is capacitive coupling, which establishes a return path through the air, through electrostatic coupling. And this can be thought somewhere in between the other two. This has a few advantages, so it can actually do hand-to-hand communication, as we'll use in our device pairing scheme. Also, it only requires one electrode to be in touch with the skin, and it's fairly resilient to the electromagnetic interference from outside the body. So the adversary model, the adversarial environment we consider for our device pairing scheme is as follows. So we have an attacker whose goal it is to remotely pair to one of the devices, or to subvert an ongoing pairing an ongoing pairing process between two devices. We assume that the attacker does not have physical access to the device, otherwise he could just simply pair the devices himself. He has access to the wireless channel, however he can only listen on the body channel, because we assume that the body channel, once it's established, as you can see in this picture, by a human touching the two devices, the devices can extract certain physical properties that allow them to decide whether the message has indeed traveled through a human body or it's from an external transmitter. This essentially then makes the body channel read-only for an external transmitter. So assuming that this kind of property, this read-only property holds, we can then design the following pairing protocol, and I think the first stage of this is just standard Diffie-Hellman key exchange. I think most of you are familiar with this, so I'll just keep it brief. So the devices exchange their identities, nonce, and their share of the secret key. And once they finish the first stage, then they of course hold the key. However, they don't know with whom they're sharing this. And then the second stage of this pairing protocol comes into play. So the key exchange actually only runs over this potentially insecure wireless channel, whereas the key confirmation is then run through the body, those blue arrows you can see. So what the devices do, they compute a message authentication code that's keyed with the key they have agreed on in the first phase. And the MAC is computed over the identities and the nonces. And the receiving device then not only verifies this message authentication code, but also verifies these physical properties I've talked about. And if they do this mutually, then they can conclude that they indeed share a key. So obviously, these kind of if the attacker does not have physical access to this channel, and indeed this read-only property of the channel holds, then we can say that this protocol prevents remote pairing, because the attacker might be able to establish a key remotely, but the attacker cannot successfully run the key confirmation phase with one of the devices, because we assume it's read-only. Similarly, man-in-the-middle attacks can be prevented because an attacker cannot just run the protocol separately with each of the devices, because this would be remote pairing, and also he cannot subvert an ongoing pairing process, because this will require injection in the body channel, which of course doesn't work if the channel is read-only. So obviously the security of this scheme entirely relies on this read-only property. So this is something we need to look into, because the receiving device needs to be indeed able to decide whether a message has indeed traveled through the body and is from another device that the user involved in the pairing is indeed touching, or the device is being emitted by an adversary and directed either to the receiving device itself or the body. So we have to make sure that we indeed make this distinction, because the receiving device could be in touch of the body, which is the case if there's an ongoing pairing operation. Why this is important, we'll just see in a few moments. So we then set out to experimentally verify if this read-only property is indeed true. So what we did is we built a proof of concept prototype for a body channel transmitter and a body channel receiver with lab-grade measurement devices. The transmitter is essentially just a waveform generator, and the receiver is a software-defined radio. The interface for the capacitive coupling was designed with two small aluminum sheets. One of them is the electrode that emits the signal, and the other one is the one that's floating and provides the return path for the capacitive coupling through the air. The parameters of our system, it operates at the frequency bandwidth of 500 kilohertz to 3.5 megahertz, so fairly low frequency. The sending power was less than 5 milliwatts at the peak-to-peak voltage of 3 volts. And the current we measured through the body is on the order of 10 microamperes. So what needs to be noted here is that these are actually fairly standardized process in this circuitry, and also the radio front end that's required for this setup could be miniaturized and actually produced for fairly low cost in a single chip. So since this body channel is a fairly new technology, at least in computer science or device pairing, we had to, of course, first make sure whether transmission is possible. So I'll just briefly go through this. So we chose a simple encoding and modulation mechanism, which is just on-off keying of an Manchester encoded data stream. But however, instead of just transmitting at a single carrier during the on period, we chose to transmit a frequency sweep. Well, this will later then allow to actually characterize the channel. I'll come back to that in a second. The error rates we measured were fairly low, which means error correction might not even be needed, and the throughput was remarkably high. We can actually transmit those two message authentication codes, assuming they are 56-bit length, we can transmit them just under a quarter of a second. User safety, I just mentioned it already. We never measured more than 12 microamperes current through the body, which is an order of magnitude smaller than those commercially available body fat measurement devices you might see, body fat scales. So how do we actually then characterize this channel? So luckily, some of the energy transmitted through the body channel is lost due to two factors. First one being the capacitive coupling, and the other one, the body is obviously not a perfect conductor. So the sweeps we then sent out as a part of the data transmission can be picked up. What you can see here in this figure is the frequency plotted versus the attenuation. And we can see a very distinct pattern for the body channel. The colored lines are for three people, part of our test subject population. And you can see they have a very reproducible and specific attenuation pattern. The small bumps are basically imperfections of the measurement setup, because it's quite hard to come up with a setup that perfectly decouples both devices. So we then concluded that the most specific frequency is to distinguish or to characterize this channel are those 500 kilo from basically 500 kilohertz to 3.5 megahertz. So how did we then set out and design this experimental analysis and actually to figure out whether this read-only property indeed holds? We decided to approach this from two angles. First one, we tried to classify the messages according to their origin. And the second one, we tried to actually inject messages into the body channel. To evaluate the classification, we designed two classes. The first one consists of sample of actual intended usage of the body channel, and the second one being injection samples. So how we did signal injection, we chose different emitters. We chose directed antennas, very big aluminum sheets and rod antennas, and we positioned them at various distances. The results that we got were quite remarkable. So on the left-hand side, you can see the false positive rate. That's the rate at which we were able to actually detect an injection. The rate at which a detection was actually passed as an intended use. So obviously, closer to 0 is better, versus the true positive rate, where we show the recognition rate of an actual body channel. We also did this for two body poses, sitting and standing, and just sitting only, to rule out that the body pose would have an effect. And as you can see, both lines are fairly close, so we were able to successfully rule this out. On the right-hand side, we can actually see a breakdown of some of the injection attempts, and we can learn three things from this figure. The first one is obviously the closer the attacker is with his equipment, the more likely it is that to actually generate a pattern that resembles a body channel, which comparing the turquoise and the orange bars. And the second fact is that a rod antenna, for instance, is much less likely to inject the signal than an aluminum sheet. This is due to the fact that an aluminum sheet, the big aluminum sheet, has much more capacitance, so naturally capacitive coupling works much better. And the other one is a distinction between a person touching the device or the device by itself. And it's quite remarkable that if the person touches the device, the chances for injection are much higher, and this is due to the fact that the body actually has an antenna effect. So at very low frequencies, the body helps picking up those signals. We did not just want to rely on classification, as we have heard in previous talks. I mean, there are all sorts of attacks that can be carried out, like adversarial machine learning, and so we also wanted to physically model this channel. So what we did is we modeled the human as an approximation with 3 cylinders, which is further divided into units, and these units can be approximated with a lumped network model with 2 capacitors and 1 resistor. The parameters for these network elements can usually be found in medical studies conducted on dead bodies. And the advantage of such a model is that we can now literally place the transmitter or the receiver anywhere on the body and simulate what the attenuation or pattern or these characteristics of the channel will look like. But also we can simulate attack scenarios. So together with the results we got from the classification and this physical model, we concluded that this read-only assumption indeed holds if there's at least 50 centimeters between the attacker's equipment and the body plus the devices that are being paired. Yeah, and with this, I would like to conclude my talk and just briefly reiterate what we achieved. So this is a fairly novel approach for device pairing that relies on intra-body communication. And following such an approach, pairing becomes very, very simple because all the user needs to do is literally touch 2 devices. We also were able to characterize this channel, and we found that this body channel is indeed read-only if there is at least a gap of 15 centimeters between an external source and the body. And lastly, this is a solution that also is viable in terms of manufacturing cost and form factor. Yeah, and with this, thank you very much, and I'm happy.
Great work. Jun Han from Carnegie Mellon.
Yep.
I really find this work interesting, but can you comment on the practicality of your work? Because a lot of the devices don't really have the electrodes on the devices. So what is the, I guess in your opinion, what is the advantage of using your approach as opposed to other available sensors in the devices?
So I think one of the big advantages is there's very little error, especially for even unskilled users, because it's quite easy to just literally explain someone. If you have to touch both devices, they will then be able to communicate with each other. This is kind of the first I'd say big advantage, and the other one being, of course, that we're able to kind of characterize this channel. And in a sense, it's quite logical that we can kind of, this is somewhat similar for every user because every user has roughly the same arm span, and this is kind of really something that you can characterize. And we think, yeah, this is literally just something you carry around with you anyway. So yeah. And
are there any differences in terms of the accuracy if you are wearing certain wearables? I mean, a lot of the wearables now have electrodes in them. I was just wondering if that would affect.
Yeah. So channel. Yeah, that's a good question. So if these electrodes actively induce a current, then it can indeed disturb this channel. Obviously, also if you're very close, let's say to an iron or iron plate, or if you're literally sitting on a tanning chair, an iron tanning chair in your bathing suit, then this might indeed disturb the channel, for instance. So there are scenarios where this might not be so very applicable.
Cool. Thank you.
Thanks.
Hi, very interesting work. So I've been considering the case where a lot of the kids nowadays are using these technologies, and as they grow up, their bodies change. Do you think that will affect in any way this approach?
Yeah, this is a good point, as we have a few parameters, obviously, because their arms will grow longer, so expected that this will slightly change. So we were restricted with our ethical approval to only include adults in our test population, but this is indeed something that changes. But I think you can expect this with a lot of, like, even though authentication techniques, for instance, that this will change, but then stay fairly stable over time after we reach a certain age. Yeah. No worries.